Well, it's time. Welcome back, everyone. And thanks for making it on a tough day right before the upcoming spring break. For today's work, we're going to finish off 5.2. We really finished the notes, but we threw in an additional example that's going to tie in some of the problems and methods we'll be dealing with in section 5.3. We're still doing induction. We're making a slight tweak to it. Now it's called strong induction. And its purpose is to handle more different kind of formulas. Things are defined in a recursive way. So that's going to be the major theme in section 5.3. But aside from that, any questions or comments at all, folks, to start us out today? Okay, well, let's get started. And maybe a bit of advice for the upcoming spring break. After we get through the break, we still have 6 more weeks of the semester to get through. So a lot different than fall semester, where after Thanksgiving break, the semester is basically over. There's like 2 weeks left or something like that. So if you're a little bit behind on homework, anything along those lines, this week here is a golden opportunity to get caught up. I'll be checking my email every day of the week. I'll probably be off the computer most of the time, but if you have any questions, send them out at any point. And I'll be checking the email on early mornings, responding to you, getting caught up on any grading that comes in. If you're behind on assignments, I'll accept them for full credit. And again, this is a great opportunity to get caught up. But here's where we left off. We got through pretty much all of our induction problems in these notes. We landed on the last problem where we were discussing factorial. And so now this is another take of the factorial function. Just for the sake of review, if we write down something like n factorial, we mean take n multiplied by n minus 1 multiplied by n minus 2 until we get down to 2 times 1. So that's one way to define factorial. Typically, people define it by saying 0 factorial is 1, 1 factorial is 1 as well, 2 factorial, you could say it's 2 times 1 or it's just 2. And then 3 factorial, you could say it's 3 times 2 factorial. That'd be 6. And then so on. 4 factorial, you could say that's 4 times the prior value, 3 factorial. So you would get this kind of recursion descending down when you work through the factorial. And that's the idea with how we define this factorial function here. We specifically avoided any kind of for loop and defined factorial by doing an if else. If n is 0, that means we're doing factorial of 0, and we should be getting a 1. So we returned 1 on that output. Then if we pass some other argument to this function, say 5, we skip this block, we go to this block, and we're going to return 5 times factorial n minus 1. So we call the factorial function again. This becomes a 4, but that's essentially what this is doing on the right. So we ran this a couple times to show it gave the right output for a couple test values. But now this is where our induction method really shines. You can imagine that this might be a more complicated process where recursion's involved, and induction is a great opportunity to just prove once and for all, whatever code you wrote down is going to run as intended. So we're going to do just that. We're going to prove that this function wasn't a lot of lines, but it's kind of mysterious when it calls itself at the same time. We'll prove that it returns n factorial, and we mean now for all inputs n. Any questions at all, folks, before we get started about the code itself or otherwise? Okay, let's start this out then. Because we have a specific form on how our author writes the induction method and strong induction, let's begin by just defining the predicate function. Let's loop it right in immediately. So we'll say let P, it's going to be defined from the domain of discourse. This time we do begin at 0, since 0 factorial is our starting point. So z greater than or equal to 0 into the Booleans, true, false, be defined by P of n is going to output to either true or false, depending on this statement. We're hoping it's always true, and it's going to be the statement that fact n, where fact is just our shorthand for factorial, fact n returns n factorial. So there's our predicate function, and what we're really trying to prove is prove that for all n in the domain of discourse, z greater than or equal to 0, P of n is true. So we just abbreviate it with a universal quantifier Pn. So that's our statement to prove. Let me take a quick screenshot of this. So I wrote that kind of big. Oh darn, let's just take the whole thing then. Okay, we'll work with that on the next steps. There's really two steps to an inductive proof. The base step, let's call this base step. We have to show that it's going to work at the minimum value in this universal quantification. So we begin by saying let n equals 0. On all the other problems we were looking into, we started with n as 1, only because the formulas weren't valid at 0. But this one is, so that's our starting point this time. But again, it's just going to be the minimum value of that domain. When n is 0, we're trying to prove this statement. Factorial n returns n factorial, the actual mathematical function, where this is our pseudocode. So we're kind of doing something similar to what we did in the very first section of the course. We wrote down pseudocode for a summation, and then we traced it. Here, if n is 0, we're going to trace through this code and see what happens. The immediate thing that occurs is that block is executed. So let's say that's right here. Let n be 0, then the if block, there's only one, so we can say the if block is executed. And when that's executed, there's not much happening. We have an immediate return value. It's executed and returns 1. So if we're returning 1, essentially what we're doing is we're trying to show that this is true at p at 0. We looked into the left-hand side in a certain sense. Think of returns as just saying equality, essentially. The left-hand side, we returned a 1. The right-hand side, just like on all the other proofs we did, we're putting 0 there. So we'll say also 0 factorial. Let's write it this way just to really show how it's involved. And factorial becomes 0 factorial. By definition, 0 factorial is in fact a 1. So we matched the values. The pseudocode returns 1. 0 factorial is also 1. So we can now say this shows the predicate function at 0 evaluates to true. So that's 1 down, infinitely many more to go, but that's the base step. That's our start. Any questions at all, folks, running through this first portion? Okay, it definitely feels pretty weird because all of our other induction proofs, we were trying to prove some kind of mathematical formula, summation formula, or maybe a divisibility relation. That was what we were working on. But now in this application, we're trying to show this pseudocode is the right algorithm to implement factorial. So it feels different. If you study the steps that we took on all the other problems, they're 100% parallel so far. And let's make sure that happens with the remaining steps. Let's shrink that down just a little bit. We just need it for a reference as we just write out the next steps. The next steps are the inductive step. What we always did on the inductive step is whatever value's here, we increment by 1 and say let n be greater than or equal to that next value. So let's start by saying let n be greater than or equal to 1. Now we make an assumption. Let me make sure I have my color coding exactly before. We're going to use blue. I forgot that. I was going to go for green. We're going to make an assumption in blue. Assume that P at n is true. Assuming that's true, oh, hang on, made a mistake there. We want to go n minus one. That's a similar mistake I think I made in the first problem in the notes. Go n minus one is true, with the goal of proving P at n itself is true. So why n minus one? We plug this minimum value, if n is in fact one, you get P at zero, it's already established as true. The n could be two, it can be five, it can be 10 to the power 30 minus one, something random like that. So an arbitrary integer greater than or equal to one, we're assuming that's true, but that means we're just assuming that occurs, but for the right value of n. So let's write it down. This means fact n minus one returns n minus one factorial. So we've got that statement down. That's our inductive hypothesis, we often call this. Now what we need to do next is we must show P at n comes out as true as well. If we can show that, we have proven the actual code down here will run as intended. Now, it might not run correctly if we make some mistakes implementing it in, say, Python or C along those lines. But we're saying that just this algorithm right here, as presented, make the tweaks to make it work in your language of choice. This will run and always give back true here, meaning we get n factorial in fact. So we're trying to land on that statement there for P of n. The way we do it is we trace the factorial function again. So notice that this time when we're tracing it, we have a big assumption. If n is greater than or equal to one, we're not going to execute this block whatsoever. So making that statement was actually really critical. What happens is the else block is hit. And that'll happen for any value here we choose on n. So let's say that next. Next, since n is greater than or equal to one, the else block is executed and returns well, it was a very short block, one line. The return is this. It returns n times another function call, factorial, n minus one. And if n is large, this could be a lot of function calls because it's recursively defined. But we don't have to work super hard because we know something about factorial n minus one. Wrong color coding, let me try again. And the inductive hypothesis here, when we assumed P n minus one is true, we're also assuming factorial n minus one returns n minus one factorial. So we can substitute that right here. And you could write equality if you'd like, but this is a function call. So typically the way we'd write this is we'd say it returns n times. When we say returns, we mean this function call right here. N times, swap in place of this, our inductive hypothesis, n minus one factorial. And that means our work is just about done. Because if you have n times n minus one factorial, then notice you can rewrite that. Because n factorial being n times n minus one times n minus two down to 2 times 1 means you could just take this entire thing, associate it, and it becomes n times n minus 1 factorial, where let's put in the bracket here just for emphasis, although it can be dropped. If we multiply these through, that's just another way to say factorial, but starts at the maximum integer n minus 1 rather than n. So the moment we're looking at n times n minus 1 factorial, we can say that this is, in fact, equal. No function calls here, so let's just use mathematical notation. This is equal to n factorial itself. So putting that all together finally, we just showed that, well, for some specific value of n, if we look into our factorial function defined down below here, it's going to in fact return n factorial. If that's the case, it means P of n will evaluate as true. So we can now say this shows P at n is true. And that's all we had to show here. It's kind of interesting in a way because, again, the pseudocode is kind of mysterious when we see a function calling itself once we're writing that same exact function, that this does the job. This really implements the true factorial function. So once we assume that this is true, we conclude that P at n is true as well. We can make some kind of final declarative statement. We could say, because n greater than or equal to 1 was arbitrary, and P at n minus 1 implies P of n, that means a proof is complete by induction. Or since we've seen a lot of induction proofs, you could just end it right here and say, this verifies the proof. Let's let this one be short. So we want to show this, and we've in fact done it. We've showed for any integer, infinitely many different integers, you plug into this function, it will always return an n factorial no matter what. Well, that was another look at induction, ordinary induction, now using recursion. And so now we're going to look into other kind of problems where recursion comes up again. We'll write some pseudocode in some problems, and in some problems we'll also prove the pseudocode returns what's intended using these same kind of arguments. But any last questions or thoughts, folks? Getting through this one? Okay, again, this is where induction really shines. It's a clever technique that can prove a lot of interesting mathematical facts. But if you have some kind of algorithm that you write down in pseudocode, it involves recursion. That's why we're kind of strong on that emphasis there. Induction is just a natural technique to show it runs as intended. So let's now switch gears. We're still doing induction problems. The proofs are going to look very, very similar. But some of our recursion problems just require a little bit more than the induction technique that we saw. And that little bit more is the so-called strong induction. There's a revision here on these notes. I noticed just this morning that should have been an A1. I wrote it as an A sub 0. So sorry for that edit right in the middle there. The notes on Canvas have been uploaded with that revision. Here, just for emphasis, I put in proof by induction because that's the technique that we're changing. I wrote it's a powerful technique, but it's not well suited to all inductive proofs. Sometimes in the inductive proofs we'll see on these notes, you have to make the assumptions that both Pn minus 2 and both Pn minus 1 are true. Not just that step, we need sometimes a little bit more, 2 prior assumptions. And in some inductive proofs, you need even more than that. So if you're assuming beyond that statement there, that's when it becomes strong induction. So I emphasized this situation because these are the proofs we're going to take a look into in our class. It's an extension of this part right here. We have the same goal. We're trying to show P of n is true by making some assumptions. We still have a base case, but sometimes there's multiple base cases that we have to show. And this is what the proof by strong induction is going to look like. We'll say, suppose we want to prove some predicate function holds in some domain. We're writing down one definition, so it's like the last problem we did, but for some problems, depending on the formula, the notation, that 0 there could be a 1. It could be a 5, just depending on which kind of problem we're looking into. So it says to give a proof of the universally quantified statement, this is where induction and strong inductions shine. In strong induction, we have multiple base cases. We prove as many values here as true as necessary for some integer k. For our problems we're going to look into, it's pretty much going to be the two base cases. So again, we're not going to look into some of the crazy strong induction proofs. There's some pretty wild ones. For example, in the fundamental theorem of algebra, the proof that any integer you write down is either prime or can be uniquely factored as a product of primes raised to certain powers, you have to assume multiple things, and you have to use all of this, every single assumption, up to n-1. But for us, we're going to make two assumptions here, land on that as a conclusion. So that's how our proofs are going to go. So same similar idea. We're making more than one assumption. We're going to assume two prior cases just because of the format of our particular recursively defined sequences, and try to show the predicate at n is true. Well, any questions so far, folks, with the new landscape so far? Okay, again, it's a pretty general technique. The way it's been written down is extremely general as well. But because we're not trying to prove really hard topics like fundamental theorem of arithmetic, that's a pretty interesting and wild proof. Really belongs in, say, a chapter like number theory. This is going to be the base cases will show that p at 0, p at 1 is true. Or if we have to reindex, we'll show p at 1 and p at 2 is true. Then we make two prior assumptions, again, re-indexing these as necessary to show p at n is true. In fact, we'll keep this format similar. We just have to start at 1 here and go to 2, because on this domain, we're looking into a sequence that starts at 1 itself. Well, example 1 is kind of interesting because it gives us a sequence. This is a list of numbers, an infinite list. We have a at 1 comes out as a 1, a at 2 comes out as 4, but all the other values in the sequence, going from 1 to infinity, just a list of numbers, are defined recursively like this, much like how the factorial function what can be thought of as a recursively defined function. And I'm not too sure what happened here. I think I hit something that put in a date automatically. Just noticed that. Sorry for that distraction there. This recursive definition holds for n greater than or equal to 3. Okay, so that's what we're trying to prove so far. But first, we're not trying to prove this. First, we're coming up with the formula for a sub n. Then we'll define through strong induction that the formula that we come up with, that we're going to, sorry, just kind of getting mixed up in my words. We're going to come up with the formula, conjecture formula, an educated guess. Then we'll prove that the formula is true, is what I was trying to say in the next parts. Looking at that, some folks might already have an idea of what a formula could be. So if you have any suggestions on what a good conjecture is, a good educated guess, don't hesitate to throw it out at any time. If you're not sure, the best place to start is let's find more terms of the sequence. We really only have two. It's an infinite sequence, and it goes 1 is the first term, 4 is the second term, and if we want the next term, we have to compute A3. Let's do it down here, maybe over here. A3, the third term, has to be done recursively like this. It's 2 times. It goes AN and then 1 less. So here it's going to be A3, 2 times A2. So it refers back to the second term of the sequence. Then minus. If it's AN, say 3 here, you take 2 off that, so you're taking A1. Add 2. So that's the format for the third term. Now we can plug in values. This is going to be 2 times, we have a value for A2, minus A1 is 1, plus 2. So this is 8, plus 2 is 10, minus 1, 4A, 9. So that's our third term. There's infinitely many more. But so far with a 149, I wouldn't notice any patterns at the moment.
Yeah, add 3 and then add 5.
Add 3, yeah, we have +3, +5 on this one, which would possibly suggest if that pattern occurs, add 7 on the next, right? Getting us to a 16 in that case. Let's check that out. That looks like that ought to be the case. So A4, let me put down here, there's a pattern of A3, +5. If it holds, we have a +7 here on this one to get to a 16. Let's check this out with A4. A4 is going to be take 2 times A3, go back 1, minus, go back 2. So this is going to be A2 plus 2. We plug these values in. This is 2 times A3. We have that value now. It's a 9. Minus A2, that's way over here, a 4. Plus 2. So this is 18 plus 2 for a 20, minus 4 for a 16. So the pattern holds. So if this were to keep on going, we'd go +9, right? +9 would take us to 25. That sounds about right. +11 would take us to a 36. So that's a worthy pattern. So that absolutely holds. And if we're
Which
thinking
shows
about,
that the true pattern is actually whatever number squared.
yeah, good call. There's an actual increasing pattern here that holds, but the nicer one to think about, the one that's probably going to be easier to prove, is the squaring one. Good call. So this is the sequence AN, but we can also rewrite it as really it's just 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, and so on. That looks like it holds as well. We didn't really check it out on this one whatsoever. But again, we're making a conjecture. We're not trying to prove it right here. So going back on that last comment, let's say AN equals n to power 2. Because it seems like if you're looking into the first term, you're just squaring 1. If you're looking into the second term, you're squaring 2, and so on down the line for every single one of those terms. Let me fix my penmanship on that. That's A sub n. So now that's our conjecture. We're making a guess that this holds for all n in z greater than or equal to 1. Now, these things can be tricky, right? It's conceivable that the sequence recursively defined, maybe it's just slightly more complicated, that you can come up with lots of really clever sequences that can show a pattern for the first 10 terms, the first 100 terms, but then on term 101, the pattern could break. That's absolutely conceivable. It might be pretty complicated to show you've got, say, 6 terms that are squares, but the seventh term is not. This is probably a more complicated looking definition for the recursive sequence, but it could happen. So the next thing we want to do is we want to prove this really works for every single integer in that domain there. So now that we got a conjecture on paper, here's where we're going to start using strong induction. And really, it's the same kind of idea. We're going to prove the base cases. Next, we'll prove the inductive case. Once we do that, once we get through the inductive case and show P at n holds, whatever that predicate might happen to be, our work is done. We'll have proven this formula holds really for all n in that domain. Well, let's put here, we will prove this using strong induction. And why do we need strong induction this time? It's mainly because the nth term, we're trying to prove this whole thing is n squared, but it refers to two terms back. So if we try to use ordinary adduction, that's going to be really tricky. I don't think it would work out at all in this one. This makes one assumption, but we want to assume that we have a formula for an minus 1. That's this part. And then we also want to assume we have a formula that holds also for an minus 2. That's this part right here. So we're making two assumptions. Now it's strong induction. But the good news is, again, it's going to feel like very, very similar kind of work. Slightly different math because of the recursive structure, but the actual logic of the proof is going to look very, very similar. So let's go down below. Let me put this here for just a quick reference. Actually, I want a bigger screenshot. I want the proof technique and the thing we're trying to prove as well. Well, the recursively defined sequence at least. So there it is. Next thing we're going to do is define the predicate. Mainly, the whole reason for defining the predicate function is to really fit it inside the structure so we can really understand what the author is even trying to convey with all this notation. He refers to P, that's the predicate function, so we'll define it. Let's just say briefly, define P of n. We know it's going to have a domain, z greater than or equal to 1, a codomain, true, false. You could put that extra statement in like we did on our first question. If you decide to jump right here, that'd be okay in this definition. P of n is going to be the statement that an, we're talking about the nth term of the sequence. It's defined in this way, but we've conjectured it should just be n squared, a massive simplification of that definition of the sequence. So I said defined. Define that predicate. So here's the predicate. We'll write the conjecture above in terms of P, then write the conjecture in terms of P and the quantifiers. So that's just a restatement of what we said above here. Prove that for all n in z greater than or equal to 1, P of n holds as true. Just said briefly like that. So we have the predicate. This just says once again, pretty much verbatim what we set up here. Now using the predicate function, exactly what we're trying to prove. Now the proof takes off. We're going to prove the base cases indeed holds. That would be these two we have to prove. Our k value, in other words, is just going to be 1. Excuse me, 2. We're going to start at p at 1 because we are beginning at 1 on this one, and then go to p at 2. So 2 base cases. So here's what it's going to look like. Let n be equal to the minimum value in this domain, just a 1. Then we're trying to show p at 1 holds. So we go back to the predicate function. There's two sides, so we analyze both sides independently. We can say then an, we know by the definition of the sequence down here, it's just 1, so we can throw that on paper. And we conjecture it equals n squared, so let's put that out. N squared is going to be equal to 1 squared. It's also 1, so we've shown this equation holds 1 on both sides. So this implies p at 1 is true. So we've got 1 base case down. But again, we need 2 base cases. If we're using 2 right here, as we will on the next step, we're going to need 2 base cases to start this out. So now we go higher. Let n be 2. Then we don't have to calculate anything. We just have the value here. An is going to be 4. And our conjecture, we're now looking at this side, n squared, is going to be equal to 2 squared. It's 4 as well. We definitely knew that. That's what we were looking into when we conjectured that formula here. But now we know it's strictly true, so this proves the predicate function at input 2 is also true. So that's 2 down. We have infinitely many to go, but that's what we're going to resolve when we now go to the inductive case. Well, any questions to this step so far? Okay, here's where it starts to look just a little bit different. Now, usually when we did an inductive proof, if we had a value right here, we'd go one higher. But we have to go one higher than that value. We have to let n be greater than or equal to 3. And another way to think about it is, if you say n is greater than or equal to a 2 going off this value, you'd be plugging 2 here. That would work out, that'd be p at 1. If you're plugging 2 here, that's p at 0, and it's undefined. Our predicate function only takes on values starting at a 1 in its domain. So that's one reason we have to start at let n be greater than or equal to 3. So we go off that last integer there, go one higher, make a greater than or equal to statement. And another way to think about it is the recursively defined structure starts at n is greater than or equal to 3. We have to match that up. So that's another valid way to think about it. So if n is greater than or equal to 3, you can now make an assumption that all of these statements are true, but actually we just need 2 of them because it's going to be involved in those 2 portions in this recursive structure. So we'll say next, let's say, assume that Pn minus 2 and Pn minus 1 is true. So again, pretty similar to what we did in the very last section, except we're put in an and statement, so we want both of them to be simultaneously true at the same time. We say immediately what this would imply. We go back to the original predicate. We assume Pn minus 2 is true. Then that means an minus 2 is going to be n minus 2 squared. And same idea with the next one. All we're doing is swapping the index, swapping the base for the input to the predicate function there, n minus 2. Do it again for n minus 1. So same song and dance, just different value. A n minus 1 equals n minus 1 power 2. And that's our inductive hypothesis. We could also say Pn minus 3, Pn minus 4, up to P1, P at 0 is true, but we wouldn't actually use that whatsoever in the proof, because once again, we just need to make those 2 assumptions to work on those 2 steps of how an is defined in the first place at greater than or equal to 3. So now that that's done, our objective is to show that these assumptions, this right here, will imply that P of n must also be true. That's going back to this statement. So that's our goal next. Let's actually say that next. Probably deserves a new page at this point. Next. Well, we can start on one side or the other, do a bunch of algebra until you get to the opposite end. We can't use the whole equation and work on it because we're trying to show that that's true. We can't start by the assumption of its truth. So easiest side to work on is going to be the left-hand side for sure. Let's say an is going to be equal to, well, first the way of an is defined is, let me see if I can zoom out just a touch. There's an right here on the bottom. An is 2 times an minus 1 minus an minus 2, add 2. So we start on the left-hand side. We just plugged in by the definition below how it's defined. But our inductive hypothesis is powerful. It's good. It's called strong induction because we have 2 big assumptions. We can make a swap here for an minus 1 And here for an minus 2, from what we see in blue on that inductive hypothesis. So now this is equal to 2 times, for an minus 1, we put in n minus 1 squared. Then it goes minus an minus 2. But we've assumed an minus 2 follows our conjecture. It should be the base n minus 2 raised to 2, then add 2. So somehow, some way, this is going to work out, give us Pn, which is a statement that we're going to get n squared. So now it's just all algebra from here. Any questions on making any of those substitutions or assumptions? Okay, let's start just doing the typical thing in algebra. Let's expand this out. We will get 2 times n squared minus twice n plus 1 minus, same expansion as before, n squared minus 4n plus 4, then add 2. So that means an is 2n squared minus 4n plus 2 minus n squared plus 4n minus 4 plus 2. So let's see how this cloud of stuff resolves. First, n squared minus n squared will give us n squared. Next, negative 4n cancels with positive 4n. And we have 2 minus 4 for negative 2 plus 2 for 0, which means that's all we get. Somehow, some way, the algebra completely worked out to the nth term is n squared. It was only based off these two assumptions, that the 2 prior terms and the 1 prior term, n minus 1, gives us the right format, matching that structure. So once we got to this, it immediately implies P of n evaluated as true. And the only assumptions we made was these 2 prior values evaluated as true, n is greater than or equal to 3. It's fully arbitrary. We didn't check an individual case. N could be any number whatsoever that fits there. So right at this stage, we can say, since Pn minus 1 and Pn minus 2, that's kind of confusing. Let me keep the order the same. Pn minus 2 and Pn minus 1 implies Pn. We've proven that directly, you giving a direct proof, much like in chapter 3. We have proven the conjecture by strong induction. Or you could just say really briefly, after you get true here, the proof is complete by strong induction. That'd be a fine statement there. But we did it. The original sequence, where'd it go? I think I accidentally stole it. The original sequence is complicated in the way it's defined, but if we simplify it down to just being n squared, that's again not quite good enough, because we might wonder, could this pattern ever fail? If this pattern failing is critical, if this was some other much more complicated process, we need to really prove what our intuition is telling us. And this is the firm, no arguments method that would tell us that really was true. The original sequence, nothing but n squared. Well, any questions at all, folks, getting through those steps? Okay, well, that's one strong induction proof down. And for the next one, we're going to do something pretty similar, practicing with how the method goes in this case. We're going to show a different kind of algebraic structure. So the algebra in some ways is a little bit trickier, because This time we're not making a conjecture, it's been handed to us, so we're going to just check out if that's really true. Probably if it's asking us to prove it, that gives us a good idea it probably is true. We'll also write down pseudocode that implements this, returns the nth term using recursion. But you know there's two kinds of pseudocode we can give, so we'll give both. We'll give one using recursion, but you know the simplest pseudocode would just be use that, because if we prove it's true, then we don't use recursion, that's going to be the most efficient code ever, right? Fast evaluation, just an exponent to add one. After we get through that, we'll look into the Fibonacci sequence. We're going to write pseudocode that implements the sequence, run it to see if it works, and then actually prove that it's our pseudocode that we write, much like with the factorial function, really returns the nth term of the Fibonacci sequence. So this is a problem we might come back to after the break. We don't want to rush through these kind of problems. I think we have just enough time to give this one a try. So again, same kind of situation. We have an infinite sequence, just a long list of terms unending, starting with this pattern. First term is 3, second term is 5, and the nth term is 3 times the prior term minus 2 times the 2 prior terms, an minus 2. This will hold for n greater than or equal to 3. But the claim is this entire recursively defined structure, which gives an infinite list of numbers in this sequence notation here, is nothing but that. The nth term is just 2 to the power of n, add 1. That seems kind of amazing in a way, right? It's strange that this weird little equation here, not giving us n squared like the other one, they looked very, very similar. But somehow, some way, this one is giving you a function that's exponential, a completely different thing like the degree 2 polynomial. So it's a pretty bold claim. We're going to see if it really holds as true. First thing we'll do is define the predicate, so we can really work through the structure of strong induction. Let's say define P of n by the statement that the nth term here of this sequence, although it's defined this way, it's nothing but 2 to the power of n, add 1. For this part, write the conjecture above in terms of P, the predicate we wrote in quantifiers. You'll notice that pretty much in this entire chapter 5, quantifying our proof is pretty fast, unlike chapter 3, where there's a lot of variation there. Here, all we're going to say is, for all n, and z greater than or equal to 1, that's our implied domain of discourse coming from either here, the first term is indexed at 1, or from here, the sequence is indexed as 1 as well. We put greater than or equal to 1 on the domain. Then we say such that P of n, implying P of n is true. And again, if you wrote this, it's completely fine. It's a little bit stronger emphasis. It's considered redundant because that's what we're implying if we left it this way. But I'll leave it up to you how you'd like to write it. So there's 2 base cases, just like before, mainly because this recursive structure involves 2 prior terms. If it involved 5 prior terms, probably going to be a lot of algebra, but we're likely going to need 5 base cases. So we'll start at the minimum value in the domain of discourse, really kind of just copying the entire method of the last example. Let n be exactly 1. Then we go to the predicate here. We're checking both sides. We can say then an is a1, which is, just give it to us. It's 3. We don't have to compute it. And that was the left-hand side, so we verify the right-hand side. 2 to the power n plus 1 becomes 2 to the power 1 plus 1. That's definitely 3. We've matched 3 on both sides. So this implies the predicate evaluated at 1 returns true, meaning the formula holds when n is 1. Then that was so fun, we just do it all over again. Same kind of pattern. Let n be 2. But any questions at all, folks, on that first base case? Okay, let's do it all over again. Let n equal 2, then an becomes a2. We do a lookup on the sequence. That's provided as 5. So we checked the left-hand side is 5. Our hope of hopes then is the right-hand side is 5, or else the problem is ruined and we're probably going on spring break early. I don't know how we fix it unless we can conjecture something. Let's hope it works out. This is 2 power of n plus 1 becomes 2 to the power 2 plus 1. But that's just 4 plus 1 resulting in 5. So there's a match on the left side and the right-hand side of that definition here. Definition of the predicate, really verifying the equation rather, which means P at 2 is true as well. So we're done. That's all we needed to show for base cases, that the statement is rooted in reality. There's potential to write down equations that are false, yet you never detected it because you were able to prove the inductive case. The only reason it was really false was it may have not held for the base cases whatsoever. Recall, if this is a universally quantified statement, it has to hold for all values. So neglecting this step can lead to some really remarkably interesting conclusions that are totally false, all because of not doing the base case portion. But now in the inductive case, here we take the same process, the same method. We will say, let n, it's arbitrary, but specifically there's a minimum value. It has to be greater than or equal to 3, one higher than the last base case. Also, this is kind of a giveaway of what it should be. It should match that value there. Assume next, this is the inductive hypothesis that Pn minus 2 and Pn minus 1 will evaluate to true. So we're making really 2 assumptions. We go here and we'll say this means if we say Pn minus 2 comes out as true, the and is implying it, then that just means an minus 2 is to the power n minus 2, add 1, and a literal end coming from right here. New assumption, Pn minus 1 must also be true. So plug in the sequence an minus 1 becomes 2 to the power n minus 1, add 1. So that's our inductive hypotheses, that the sequence comes out correct for these 2 specific terms. Now our whole goal is to use those 2 assumptions in blue to prove it's going to hold at n now, that P of n is going to evaluate to true as well. Here's where we make our big leap of logic. And you notice a lot of this is just setup, really. Show it holds for base case in induction or base cases for strong induction. Make an assumption for the inductive hypothesis. Write down on paper exactly what it means because we're going to substitute that in. We did that on almost every single problem. Yeah, literally every single problem, we did that exact step. Then we went and said next. Now we're gunning for P at n, which means we work on the left-hand side first because I am not creative enough to work on the right-hand side, make it more complicated and get back to a sub n. Easier to work on this side because it expands to that and we can simplify it down, hopefully returning to 2 to the power n plus 1. So we'll say an equals, we can't put that in yet. That would be circular logic, so we have to go to the definition. It's valid for n greater than or equal to 3, but we assumed that, so we're on the right track. An is 3 times an minus 1 minus 2 times an minus 2. So that's just the definition of the sequence. But we know something about those terms. Here's the 2 big assumptions. So we make 2 substitutions, one here and one here. So now it's equal to 3 times, plug in an minus 1. So this entire thing, 2 to the power n minus 1 plus 1 minus 2 times n minus 2 is 2 to the power n minus 2 plus 1. So there's our substitutions, and some way, somehow, we have to land on that. That's our big leap of logic. From here, this is just it's all algebra from here on out portion of the problem. Any questions on all getting to this stage? Okay, again, let's take a small step back from this one because it's impressive how weird this problem really is. When you look at this doesn't look very different, just different constants, no constant term being added on, but somehow this gives you an exponential function. Well, a term that's an exponential function, then a non-exponential for the nth term. Whereas this one, really not too different, right? Just different constants and then a constant term entirely. It resulted in n squared, a polynomial degree 2 function. Polynomial functions and exponential functions they can't be more different. So the fact that something like this, which looks extremely similar to something like this, yet we're getting an exponential function, to me that almost seems unbelievable. But now if the math works out, we can't refute this logic. So let's see what happens when we expand this out. So, well, let's just follow our nose with algebra. Probably the first thing I would do is distribute the 3 and the negative 2. When we distribute, we'll get 3 times 2 power n minus 1 plus 3. This distribution, let's go carefully, is minus 2 times 2 power n minus 2 minus 2. Well, we can combine terms. That'll give us a positive 1. And that's good. We have a positive 1 on paper already when we combine like terms. But we have to get to 2 to the power n. We've got the right ingredients because we have 2 to the power in 2 spots. And the next thing that's helping us is these are like bases. This is really 2 power 1 multiplied 2 power n minus 2. We can add those together, add 1 to that exponent, and this is what we get next. 3 times 2 power n minus 1. And I'm going to combine these to a plus 1. Let's write it over here. Then go minus. Combine these together, add the exponents, and we get 2 to the power n minus 1. So not a whole lot of steps. We've combined bases. I added the 2 like terms here to a plus 1. And now this is the next thing we get. Well, we have to do something algebraically. Anyone have a suggestion on what we could try next? Recall that's pretty much our goal, right? 2 to the power of n has to be in one spot. We have n minus 1, so that's a problem, but even worse, the base 2 is in 2 spots. But we still have one good trick. If the thing we want has to be in exactly one location, like we have here, a base 2 in one spot, you can factor. There's a greatest common factor, 2 power n minus 1, here and here. So if we factor that out, we would get 2 to the power n minus 1. When it factors from here, it leaves a 3. When it factors from here, it leaves a negative 1 plus 1. So I factored out to the greatest common factor to the left. Now we have more like terms, and really these were like terms, so you could have just speed lined to the next step, skipping the 1 in the middle. But on the next step, let me drop a line. We have 2 power n minus 1 times 2 plus 1. But that's fantastic. We have base 2 in one spot. And even better, they're like bases. This is 2 power 1, adding 2 to the power n minus 1. That means the exponents add together, and this is just 2 to the power of n plus 1. These resolve to exactly the thing we wanted. And the algebra would have never worked out if this was different in any way. So that 3 being there, that negative 1 being there, which came from this 3 and from that negative 2, some algebra worked it out to a negative 1, were critical. Change those numbers a little bit, and there's no way this would have worked out to this. But somehow, some way, again, it's a pretty bizarre problem. This one became an exponential function, add 1. We showed P of n is true through this long transitivity of equality. It took us a good amount of steps. But now we can say that this implies P of n is true. And let's make this one closing brief. And so the proof is complete. So pretty bizarre problem getting onto that last step. Any last questions or thoughts, folks, on the conclusion here? Okay, again, these recursively defined structures are very, very surprising sometimes. Sometimes they hide a lot of complicated structure. The formats of a simplified version can be extremely surprising, like on this one, but they're useful things. They can be used in all sorts of stuff along the lines of finance, modeling populations, plenty of things defined in computer science are recursively defined structures. And this is just a simple kind of an algebraic problem that we're taking a look into. What we'll do next is, let's take this whole thing and show how we might implement it if we're writing down pseudocode. So this is our part B. It's kind of a revision of what we did on the factorial problem. Let me take a better screenshot. It's a second look at what we did with the factorial problem in the left section. And also it's kind of a warm up for what we're going to do in the next problem, working with the Fibonacci sequence. So we want to implement a function that returns the nth term of that sequence using recursion. And again, using recursion is pretty specific. So there's really two kinds of code we can give. This is the really efficient code if we use that formula right there. But if it says using recursion, we're thinking in terms of implementing it this way, the way it's originally defined. But just for the sake of comparison, we'll do both just to show how they go. So it's another take of what we did with the factorial function. We need a good name for this. You could call it just function if you wanted to, but then pseudocode might look a little bit weird. Because it's a sequence, I think the natural name might be just SEQ for sequence, or the full lettering for sequence. So we want a function, so let's call this is going to be equal to some function indexed at n. And recall, this is just pseudocode. This is meant to be code that's adaptable into any language that you personally work with. So if you're working in C++, this is probably not going to work at all. You probably have to put in lots of different kinds of ways to initialize what your input even is in the first place. Probably a whole different structure for defining a function as well. But this is just a rough and fast way to put it down on paper. So I'm going to say it's going to be a function. The bracket here is going to be the definition of this function. And let's see what we have to do. It's going to depend on n, what we're going to return. If it starts out at 1, that's going to be our minimum value for this function. Notice we're totally skipping all the error checking. So if someone plugs 0 inside this, it's going to be some odd behavior for sure. And if you wanted to put in error checking, that's up to you. You don't have to go above and beyond in the pseudocode. We're skipping just to implementing this sequence. So we'll say here, if n, this is a comparison check, so we'll use the double equals. If n comes out as a 1, we want to return the first term of the sequence. It's defined to be 3, so we return 3. So that gets us started. But we have really 3 different cases, right? There's a trichotomy here with the way it's defined. So I'll use if and then else if as the next structure. Else if n is equal to 2, we're going to return the 5. Return 5. And then that entire block is done at that stage. So here's the third part of the trichotomy. On this one, n could be either 1, it could be 2, or it could be greater than or equal to 3. So this is the third case we're looking into. We could just say simply else, and then plug in a 3, 5, a million. It's going to execute right on this block. Else, return something different this time. This is now the recursion part. We want to return this as a structure. But I can't put an minus 1. There's no way the pseudocode would make any sense at that point. I have to use things that are already defined or about to be defined. So we call the function again. We're going to take 3 times the sequence at the input n minus 1. Then subtract 2 times, that's function call again, sequence at n minus 2. That concludes the else block, and that's the whole definition for the function. Again, if you plugged 3 inside of here and you trace this out, they'll skip the first 2 blocks. They'll run right here. Then, if you had a 3, it's going to call the function again, add a 2 right on that spot. But when it does that function call, it's going to execute this block and return a 5 right in this portion right here. It's also, if you plugged in a 3 to the original function call, going to have a 1 here. It does another function call of itself, but it executes that block. When it is 1, you get a 3. The more complicated traces are what happens if n is like 10. That trace is going to take pages. If n is 10, then here, this block is going to run. You'll have to do the sequence at 9. So that it's a new trace at 9. You come back here. This is going to run. You have to do the sequence at 8 and at 7 as well, which means you start over and over again. You can imagine this just gets nested down, down, down until you get to the base cases. These are where the computations start to come together, and then it builds up the output, storing intermediate values as it goes. But really, that's the whole logic of proof by induction in a really strong way. Pseudocode here is the analogy for everything that we did here on paper, trying to trace an evaluation of like this for some arbitrary n. So that's how you would define the sequence if we're using a recursive definition. I feel like it's an odd thing to ask, right? Because if you were doing something like this is a lot of compute power potentially, and that's efficient. So it doesn't go along with the spirit of the question. Let's put it on paper as well. Option 2 would be sequence efficient. The long name, but it's efficient, so it's worth it. So let's go with that name. Will be function taking an argument n, and it's going to do nothing but to return 2 to power n plus 1, written in kind of a way you might put in, say, like a TI-83 calculator, or write down in a computer programming language. So this one is really efficient. It does the same exact job, and that's because we proved it works. Sometimes coming up with these things are kind of tough, and that's what we're going to be looking into with the Fibonacci sequence. There is a formula for the nth term, but it's a pretty weird and surprising looking formula. But we're going to focus purely on writing out pseudocode to implement this thing right here. And then using strong induction, we'll prove that the pseudocode really returns all the terms of the sequence. We skipped the proof on this one. This one is more just practice writing down the pseudocode for something defined recursively. Well, we've got about 5 minutes, but I think this is probably a pretty natural stopping point. The next problem is kind of long. It'll be a good one to return back to after we've had a long break. We'll refresh proof by induction and run through one more proof, this one here, before moving into chapter 7 on number theory. But any last questions or comments, folks, on the last things we've done or otherwise? Okay, well, have a great break, folks. Try not to work too hard if you can help it. If you have questions, don't hesitate to send them out. I'll be checking my email pretty regularly. Otherwise, I'll see you all back when we return on the 31st, right before April Fools. But take care, folks. I'll talk to you all later. Thanks. Have a good one. Awesome. Thanks. Have a great break.
I wanted your input on